The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: agricultural, earth and environmental sciences, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. The college has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor, and the laser is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the
Thanks,
past.
love.
The highly successful Ignite Engineering program
Please.
and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering and technology through exhibitions, festivals and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do
Excuse me, I must rest my brain now. Okay, you guys would like to make a lot of money. Okay, good day, everyone. Ajay, I'll just say a few words before we start, right? My name is Mr. Ashwin Manuel. I'm the principal ADO on the UKZN on the Pietermaritzburg campus for the College of Agriculture, Engineering and Science. Thank you all for attending today. Please, can you all keep your mics muted throughout the session? I hope you guys benefit from this. And I'm going to hand over now to Ajay Besessa, who's going to be your teacher for the session. Thank you.
Okay, I think you can hear me now. So
Yes,
these are the, thank you. These are the chemistry labs at the Westfield campus. So you can see we have very nice modern lab facilities. These are even better than some of the universities overseas. And when you come to UKZN, you are basically going to work in these world-class labs, okay? So we train you, and we make sure that you are exposed to some of the best equipment and you are well trained as far as being a chemist. So if you're going to work in any laboratory, in any industry, you are trained extremely professionally in most of our labs. So you can see we have quite nice facilities at the Westville campus. Okay. Ashwin, if you are online, there are still some students that I have to admit. Are you able to take care of that before I start?
That's fine. Students, as they come in, I'll admit them in, Ajay.
Okay, thank you. Thank you. Okay, guys, sit back, relax, don't be tense. Let's basically be quite... and those that are connecting, please turn off your videos so that... Just turn off your videos and unmute yourself. Ashwin, I'm just going to wait for a few minutes because some people are still joining, and it's actually some of them have the videos. I don't blame them.
That's perfect. We'll wait a few minutes for more students to come in.
Okay. Right, guys. I put on the grade 12 topic, grade 12 topics, right? So organic chemistry, Okay, we've got to wait. There's a question whether you're doing Newton's law today. I'm
Chemistry, grade 12.
Oh, Ashwin, can you just mute all the participants coming in?
Okay, guys, just a few house rules. Please, can everyone keep their mic muted?
Chemistry, grade 12.
Okay. Thank you. Okay.
Okay, thank you. I think I'm back on now, Ashwin. Thanks very much. Okay, let's try this again. Right, good afternoon, everybody. Welcome to the grade 12 chemistry tuition for today. I've put on the topics for grade 12, but today, because of time constraints, I'm going to go through chemical equilibrium, acids and bases, and electrochemical reactions and electrochemistry. Okay, so yesterday I very quickly skimmed through organic chemistry, but I put on some notes onto our website, which you can access those organic chemistry notes. So please pay attention. For the organic chemistry, what I want you to do is access the notes. I've put them in order: the chemistry of alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, and esters, as well as the carboxylic acids. So you will go through them, you will go through the nomenclatures. I've put on the notes, and the pages that you see that I've referred to for these comes from a textbook called Siavula. So if you go to the Siavula website, for those of you that don't have textbooks, that textbook is free of charge. So basically, you will go through that, through those, okay? Now, I'm going to just basically start off. It's 1 minute past 8. If you have any queries, what I would like you to do is on the chat, you'll see there's a little chat button. You can raise your questions, and at the end of the session, I will go through some of your questions. But what I want you to do now, I want you to listen. I want you to listen to the fundamental teachings. I'm going to go through some examples, and I'm going to give you a very good understanding of chemical equilibrium. And the questions that you see, I need for you to understand what the questions mean and what you are doing with the information. So you can't just simply by heart all of these things and go and write your papers. Now, many of you have already gone through your work, but let's make it easy for you to understand. Let's not mix up all the concepts, okay? So let's look at chemical equilibrium. I'm now going to share my screen, and I'm going to start off the notes on chemical equilibrium and what it means. Okay, right. So let's look at chemical equilibrium. And on my screen now, you can see I've got the heading chemical equilibrium. So you know when we have a chemistry reaction, right? You start off with products. Sorry, you start off with reactants. I'm starting off on the wrong foot, going to the products. So we have reactants. And these reactants will form products. But we generally, when you have a chemical reaction, you want all your reactants to form products. So if you look at most of our industries around us, right, they make things. Now imagine if you opened a big factory and you were making chocolates, for example. So you had a lot of reactants, and at the end of the day, after that reaction took place, you only made 4 chocolate bars. You're not going to make a profit, isn't that so? So reactions need to go to completion, and that's the whole purpose. But in the world, not all reactions go to completion, right? So, for example, some reactions will not, they're very stubborn, like they're very, very stubborn. So we basically have to get those reactions to, and generally what do? We heat the reactions. Okay. So equilibrium involves reversible reactions. Now, some reactants will form products and the products go back to the reactants. So you have what we call reversible reactions. Okay. But some reactions appear only to go in one direction and are said to go to completion. Okay. So when reactions are reversible, we show this double arrow sign. Can you see the double arrow sign? When reactions go to completion, we only have a okay. Can you see my screen now?
Yes, we can, sir.
Thank you. Okay, thanks everybody. All right. Right, so all reactions are theoretically reversible, but in some cases the reverse reaction is very slow. Those of you that can you please mute your apologies. Some of you are on this, please mute your mics. Can you? Thank you. Right, so these are just diagrams. I'm going to go quickly through to them to show you what it means and how reactions takes place. So let's just look at A moles of A plus B moles of B going to the forward reaction. Can you see the arrow is only going in the forward reaction, meaning that it only goes to products. Okay, so if you look at a reaction rate versus time, you can see that in red, okay, you have a forward reaction. And if you had a reverse reaction, you would basically reverse C moles of C plus D. That's all this diagram is showing. And there's nothing else we need to know about this diagram. In other words, it's just showing you that we have in a case where you have a reversible reaction. So this word homogeneous equilibria means that the reactants and the products are in the same phase. You see it as a liquid mixture. That's what it means, nothing else, right? So this diagram is showing you that if you have a forward reaction, in red, you can see the reaction is going in the forward, and then it forms this black line. And then what happens is when the products are formed, it simply goes back to the reactants. That's all it's saying. And let's leave it at that. Now, at equilibrium, that means when the forward reaction, so that means your reactants form products and your products start to form reactants. So it's like a swing, like a swing. You go up and down, up and down. So like that, you have reactants going to products and products going back to reactants. Now that's what we call an equilibrium, right? So the rate of the forward reaction is equal to the rate of the reverse reaction. So the overall composition of a reaction mixture does not change, right? So that means when you have a reaction mixture, the overall composition is basically, there is no change, because as soon as you form the products go back to the reactants and so forth and so forth. So let's not worry too much about that. But individual molecules go on reacting, right? So we call that dynamic equilibrium. If you haven't done this in terms of your notes, don't worry too much. But all you've got to remember that you have a forward reaction and then you have a reaction in equilibrium. So we want to know what is this equilibrium and what it means. As long as the temperature and pressure remain constant and nothing is added to take from the mixture, the equilibrium remains unchanged, right? So you don't change that system. Now, look at this diagram. It's a very simple diagram. Can you see that red line? Okay, can you see the red line? That means you're basically starting with your reactants. So your concentration, that means if you started with A and B as reactants, can you see what has happened over time? It's actually dropped to 0. That means you got no more reactants left. And the blue line simply shows you that you've got products, right? So as your red line is decreasing, right, your blue line is increasing, which is C plus D. That's all it's saying. That means you can see that the reaction goes to completion. So this is a reaction going in the forward reaction. Okay, and in most of our cases, you find that we have reactions that want to go to completion. Okay, now in some cases, you can see that A and B, right, are the reactants. And this is an equilibrium reaction. You can see the double arrow there. So that means what's happening is some of the A and B gets reacted and only some of the products are formed. So at a given state, you can see we have reactant molecules are greater than product molecules. So you've only formed a little bit of product. Can you see that? That's what this means in terms of the diagram. So, and these things take place. Now, in this case, what are we saying? That the reactant, so in this case, you can see the red line is sitting at higher levels. That means not most of the reactants that are formed products. So we form very little products. This is where I told you you'd only form 4 chocolate bars and you'll have to close down your business. Okay. So most industries, they want to finish up all their reactants and form all their products because obviously they want to make a profit. Isn't that so? Right. So in this case, you can see the reactant molecules, okay, so the product molecules are more than the reactant molecules. But what you notice here, that the concentration of the reactants has not come down to 0. That means all the reactants has not been completely used up. Okay. So in that case, what you do is we stir the solution, you heat the solution, you put a catalyst. So in that case, you see how we can move the reaction in the forward direction. Okay. So now we have that in mind. And then we talk about this Kc. And we talk about an equilibrium constant. And now we're getting to the crux of where we want to be. Okay. So can you see the reactant A and the reactant B? And the small letter A and the small letter B are what we call the stoichiometric coefficients. In other words, if you got 2 moles of HCl plus 3 moles of NaOH, you see, that's what I'm talking about. So it's called the stoichiometric coefficients. It's just the number of moles of A, and B is the number of moles of reactant B, giving you product C and product D, right? So what does this mean now, right? So Kc is the equilibrium constant. And you can see it is basically the product of the reactants raised to the stoichiometric coefficients. Can you see? C raised to the power C and D raised to the power D over the reactants. So it's basically the products, it's the multiplication of the concentration of the products over the multiplication of the, so I don't want to say product of the products of C and D over the product of the products of A and B because it confuses. Okay, so it's basically the concentration of product C raised to its coefficient, to its stoichiometric coefficient, times the concentration of a product D raised to its stoichiometric coefficient all over the concentration of reactant A raised to the power of its stoichiometric coefficient A times the concentration of B raised to the stoichiometric coefficient of B. Sometimes in science, it takes a lot just to say this, where we could just say Kc is equal to C raised to the power C times D raised to the power D over A raised to the power A and B raised to the power B. But if I'm supposed to say capital C raised to C and capital D raised, so that sometimes it just gets a bit complicating. But let's understand what it says now. Now, I want you to look at Kc, right? If you've got, for example, a large amount of products and a small amount of A and B, right? So you can see that Kc is going to be large because it's directly proportional to C times D. Everybody see that? Don't say yes, I know you're nodding your heads, right? That means if K is a large number, that means the reaction went in the forward direction and you got a high amount of C and D. So that's why we said here, can you see? If K is greater than 1, the products are favored and the forward reaction is favored. Are you with me? Good. If K is less than 1, that means we got a larger amount. Can you see the numerator will be higher and the denominator will be higher and the numerator will be smaller. So all you need to understand here, if you've got a larger numerator and a smaller denominator, that means the product goes in the forward direction. If you've got a small numerator and a large denominator, then its reaction is going in the reverse reaction. So you can see it, isn't that so? Because if K is large, that means C and D is large, that means you form more products. And that's all you've got to remember about equilibrium. If you know that, you have a good idea about equilibrium. Right, but let's see now, interpreting the equilibrium constant. So if Kc for a reaction is large, like I told you, the mixture is mostly products. If Kc is small, the mixture is mostly reactants. If Kc is around 1, then the equilibrium mixture contains appreciable amounts of both reactants and products. And you can see, if you're going to have 1 over 1, it's equal to 1, meaning you've got equal products and equal reactants. Okay, I may be going to a bit too fast, but I'll repeat it. And I think I need to just slow down in the way I'm talking, because I probably may be going quite fast. Okay, but I'm just trying to go through this so that the notes are there and you can obviously go through the notes. So let's look at this example, right? And this is the most important thing. The first thing in chemistry, when you're working with a reaction, and I want you to even write this down, that you must have a balanced equation, right? Now, sulfur dioxide reacting with half a mole. So this half is actually the stoichiometric coefficient. Can you see we wrote it there, raised to the, so O2 raised to the power half, okay? And generally for equilibrium, we always specify the temperature, right, at 600 degrees, because equilibrium reactions are temperature dependent, okay? So you don't have to really worry about that about now. So in this case, by the way, this reaction here is part of the contact process, and it's the second stage of the contact process. And you know, this reaction here is very exothermic. So it gets very, very hot. That means the delta H is very high. Don't worry about that, because I just know this because I teach this in one of my industrial classes. Right, so it says, now we wrote a Kc, and very simply, that's the first thing you do, is write out the Kc. Kc is the product, and in some case, you'll only get one product. Can you see that? So it's SO3 over SO2 times O2 raised to the power half. Now for SO3, we raised it to the power 1, but we don't show the 1, okay? So you all know that. Now you can see, you basically have SO2 plus O2 going to SO3, and SO3 going in reverse to give you SO2 and O2. And this is one of those reactions where that can happen. Okay, so let's look at another reaction where you can see this here is a very nice reaction. It's a reaction that's sort of a hydrogenation reaction, and I think it's called the shift, the Bosch reaction, where we use it in at Sasol, you know, in the Fischer-Tropsch process, where they make methane gas. And methane gas is used, you know, a lot overseas, basically for heating in their gas stoves and things like that. So with all the load shedding that we have, we should actually, because most of the European countries work on methane gas, and this reaction you can see when you have this hydrogenation reaction, you basically form methane gas and water. So water in the form of. So if I write out a Kc, can you see? Don't forget to write H2O because it's in the gaseous form. So Kc is methane times water, the products, over CO, carbon monoxide, over hydrogen. And again, you can see it's raised to the power 3, which is the stoichiometric coefficient. Can you see that? Right. So now, for example, if you have a starting concentration of 0.1 molar CO, and if you have 0.3 moles of hydrogen, can you see that's the starting concentration? Big M, and big M stands for molar or moles per dm cubed. You did that from concentration. And we talk about an equilibrium concentration, meaning at equilibrium, that means when CO and 3CH2 goes to form CH4 and H2O, it goes back, okay? So can you see we have a starting concentration of the reactants, and at equilibrium, you have 0,0613 CO left. And at equilibrium, you have 0,1839 molar of hydrogen left. So obviously, if you started with 0.1 molar CO, and if you have CO remaining, then 0.1 minus CO will tell you how much of your CH4 is formed, okay? And you can basically see that the same amount because of the stoichiometry from CO, that will give you the amount of water formed. So that's why we're saying, so you got 0,0387 molar of H2O. And once you've got that, you can work out the Kc, because now you basically have the starting concentration. So basically the equilibrium of how much of CO is remaining, and that was the amount of starting concentration. The equilibrium of how much was basically didn't react. So a difference between 0.1 and 0.06 will give you how much of methane has formed, right? And then you can obviously now, so you know how much of methane is formed, you know how much H2O is formed, and I want you to plug that into this Kc and see if you get this value of 3.93. Okay, so I want you to do that, and you'll basically work that out. So in example 2, now what are we working with? We're working in this case, again, you can see 0.2 molar of CO, right? So we're just changing the concentrations, right? And we're changing the concentration. We're starting off with 0.2 CO and 0.3 H2O. Now you can see at equilibrium, you got 0,1522 of CO. So 0.2 minus 1522 will give you the amount of methane left, and so forth. Okay, so from the amounts of the starting, you know how much of methane, how much of H2O. So then you can just simply plug that into the K, and you would get the Kc. So you can see the Kc is 3.91 in terms of the equilibrium constant. And it's quite an appreciable value that we have. So I'm going to leave this for you to get this value. Then you'll understand exactly how it's done. It's quite easy, isn't that so? Because you got the starting concentration, and then you got how much of CH4 and H2O that's formed. So you know basically how much of CO reacted, and you know how much of H2 reacted as well. Okay, because that minus that will give you how much of that is formed. And then remember the stoichiometry. 1 mole of CO reacts to form 1 mole of methane. Okay, so in terms of the molarities, you can basically very easily work that out. Okay. Right, so let's move on. Let's look at this example. Now, I think you are used to working with this types of examples. Shucks, I think I'm talking so much I had to cough. So you can see in this example, when 1 mole, and now what I want you to find out here is when 1 mole of carbon monoxide and 3 moles of H2. Now, you know what this moles mean? Moles is simply mass over molar mass. You remember that from stoichiometry? And moles is also, when we work at the number of moles, it's in molarity times volume when we work with solutions. Remember that? So you can see here, if you've got moles and if you've got dm cubed, remember I told you molarity is moles per dm cubed. So to work out the concentration, it's simply 1 mole over 10 dm cubed. So the molarity of CO is 0.1 dm cubed, because 1 over 10 is 0.1 dm cubed. You see that? Okay, so that's how you can work out the molar composition. So when we say molar composition, it means the molarity. Okay, so when 1 mole of CO, so you're starting off with 1 mole in 10 moles, then you can work out the molarity. And 3 moles in a 10 is also 0.3 molar. So I get 0.1 moles per dm cubed, or 0.1 molar, and 0.3 moles per dm cubed, or I call it 0.3 molar. So we refer to it as molar, okay? Moles per dm cubed. And are allowed to come to equilibrium. The mixture is found to contain 0.387 moles of water. What is the molar composition of the equilibrium mixture? That is, how many moles of each substance are present. So we put in this CO and we put in the H2, and we said are allowed to come to equilibrium. the mixture is found to contain 0.387 moles of water. So even to get the molarity of water, you basically will have 0.387 over 10. It'll be 0.3. So in this case, you can work out the molarity, 0.03 molar. Okay. So you know how to work out the molar now from this particular. Right. So you can see, I want you to write it out in this particular, and I think you know, because in your textbooks and in your notes, I think your teachers would have done this with you, right? So in this case, you would have, can you see you're starting 1 mole and 3 moles? Now the change, that means when your reactants reacted, can you see you've got 1 mole? And where did I get 1 and 3? Here, see, 1 mole and 3 moles, okay? So I'm writing it as moles, I'm not writing it as molar. So when you added the 2 reactants, nothing happens. We're assuming 0 products. That means as soon as you added them, just before any reaction starts, you've got no products. But the change is now that CO is going to react with H2, right? In a reacting ratio of 1:3, right? So that means you have minus X and minus 3X, right? That means for every 1 mole of CO, 3 moles of H2 is going to be used up. And then you're going to form methane and you're going to form the water, right? So can you see? So 1 minus the amount of CO that was used, and 3 minus 3X, the amount of hydrogen. So here we know that we form 0.387 of the water. We just have to work out the X here, right? So you can see we started off with what? Now, obviously, if you're forming 0.387 moles, right? So the CO is easy because we know how much of water formed, right? So then we can simply take 1 mole of the CO and subtract the amount of water formed. Then you know how much, in terms of how much of water, how much of CO is remaining at equilibrium, okay? And the same with hydrogen. If you know how much of that you started off, minus 3 times that of 0.387, then you know how much of hydrogen that remained. So then your methane was equal to X moles, which is obviously equal to 0.387. It's a very straightforward example, and I think you know how to work this out, okay? So all you have to remember is how much you started, how much is changing, and how much is changing. How did we get 0.387? By stoichiometry, 1 mole of CO reacts with produces 1 mole of water. So if you produce 0.387 moles, that means that 0.387 moles of CO2 basically reacted. You see that? So it's very straightforward in terms of that. Then we talk about Q, the reaction quotient Q, and I'm sure you've seen this. So it's the same as your K value, okay? But it's for reactions not at equilibrium. So all previously when we're working out K, in these cases, in the previous example, we are talking about reactions that are in equilibrium, right? Now we're going to talk about a reaction quotient. You know, when we talk about a quotient, it's basically a net result, isn't that so? So whenever you see Q, it's going to be for reactions that are not at equilibrium. That means reactions going in the forward direction only. Okay, so let's have a look at an example, or let's see what Q means now. So if this Q is greater than K, that means to establish equilibrium, reverse reaction is favored. And if Q is less than K, that means we predict the direction of the reaction. To establish the equilibrium, forward reaction is favored. And if Q is equal to K, that means the reaction is at equilibrium. So now I'll show you what this means if you're a bit confused, because I know here I'm saying to you, hey, what is this guy talking about? He's talking about Q, now he's comparing it to K. So in other words, we will have a K value, assuming that it's at equilibrium. But now we're going to work out the Q, and we're going to see how to basically compare the two. Okay, Kumala, please, if you got your hand raised, simply just put it on the chat and then we'll look at your questions later. I'm just going to go through this information with you first. Right, so let's look at this example and you'll understand what I'm saying about Q and K. Right, let's go through it slowly. Now, a 50 dm cubed is the same as liter. So if you see 50 dm cubed, it's the same as 50 liters. Okay, did you know that? 1 dm cubed is 1 liter. So it's quite easy, okay? And so in this case, a 50 dm cubed reaction vessel contains 1 mole of nitrogen gas and 3 moles of hydrogen gas. So immediately you can see this is the it's part of the Haber process. Remember the Haber process to make ammonia? So in this case, we added nitrogen and hydrogen. So there's the reaction. N2 plus 3H2 giving you 2NH3, right? So now this is an equilibrium reaction, right? As you can see. So will more ammonia be formed or will it dissociate when the mixture goes to equilibrium at 400 degrees? So what we want to know is, if we put this amount into a reaction vessel, right? Will more ammonia be formed or will it dissociate when the reaction goes to equilibrium at 400 degrees? So let's see how we can. So we know that we're giving you the Kc value. That means this equation reaches equilibrium at 400 degrees. Okay, so we're telling you this and we're giving you the K. Now we are saying, let's find out if I put 50 mole, if I put 1 mole and 3 moles of hydrogen, what will happen? Right, so very easy. Oh, we didn't work that out. Okay, so I think maybe what you should do is, okay, so in this example, what I would like you to do is simply use the previous example here, starting, change, and at equilibrium, and basically then work out the value of Q and compare it to K, okay? I may have missed this out, so I'm not too sure. I'll put up this into the, so in this case, you would basically calculate a Q value from these and then compare it to the Kc. So if Q was greater than K, then the reverse reaction is favored. And if Q is less than K, then the forward reaction is favored, right? So basically, if Q was equal to K, then we're at equilibrium. So if you worked out this value and the value that you're working out here is what we call the Q value. Okay. So let's talk about equilibrium constant Kp when we're working with gases. And I'm sure you worked with gases, right? Most of you have worked with gases. So in this case, you can see all the reactants are in a gaseous phase. So here we talk about the partial pressures. That means you are mixing the two reactants. And if you have products, so this is a gas phase reaction, and we can use the partial pressures instead of concentration, right? So now you know that we talk about PV is equal to nRT. That's why you'll see we're talking about PA is equal to NA over VART. R is the universal gas constant and T is the temperature. So we can simply work at the partial pressure of the gases, right? Now, all we are saying here, you can work out the Kc or the equilibrium constant by simply taking the concentration of PCl5 over PCl3 times Cl2. But instead of writing molar, we'll write the partial pressures. So can you see? You will put the gas atmospheres of these particular reactants and not in molarity, okay? So that's what we talk about. Kp is equal to the partial pressure of PCl5 over the partial pressure of PCl3 times the partial pressure of Cl2, okay? And these are also raised to their stoichiometric coefficients. Don't forget that, okay? And then you also remember Kp is equal to Kc RT delta N. That means if you know the partial pressures, then you can work out the Kc from that, okay? Where delta N is the moles of gaseous products minus the moles of gaseous reactants, okay? So remember this. So when you're working with your reactants which are gases, then you're going to use to calculate the equilibrium constant. It's the Kp is equal to the partial pressures, and then from there you can calculate your Kc. Okay, so you can find the equilibrium constant of the gases, and using Kp is equal to Kc RT delta N, you can find the Kc of that particular reaction. All right, so if you look at heterogeneous equilibria, okay, if you look at heterogeneous equilibria, what does this mean? Heterogeneous equilibria. I'm just going to go through this quickly. That means, can you see iron is in the solid state, water is a gas. Can you see that? And equilibrium sign, you're forming Fe3O4, solid and a gas. So when we say heterogeneous equilibria, that means we have different physical states of the reactants and we have different physical states of the products. Okay, so in terms of the Kc, you can see your Kc is H. That means we're only considering the H2 raised to the power 4 and over H2O raised to the power 4, or Kp is equal to P of your hydrogen gas and Kp is equal to P raised to the power 4 of your water. So we don't consider the solids in terms of your equilibrium constants. Remember that. As long as some solid is present, no matter how much, the equilibrium is reached in the same way. The equilibrium law for a heterogeneous reaction is written without concentration terms for pure solids and pure liquids. Okay, so if you had bromine, for example, it is known as the pure liquid. You don't include it. When you are writing your exams with equilibria, please write out these K. So if you have a balanced equation, write out the Kc or the Kp immediately. Then the examiner will know that you are writing these things out. Okay. So let's look at this equation here. And you've got ethanol, alcohol, in this case it's ethanol, reacting with acetic acid to give you an ester, right? And water. So you can see we can write out a Kc. And in this case, you've got your ester, your water, ethanol, and acetic acid. So when water is a reactant or product, but is not present in excess as the solvent, its concentration must be included in the equilibrium expression. So when you get equations like this and you have water, you must, only when you're doing acids and bases, we leave out water. I will come to that just now when I'm talking about that. Okay, so if you're looking at reactions in dilute aqueous solutions, okay, so here water is the solvent and is in great excess, right? So can you see NH3, right? That means we simply took some NH3 and we added water to it, and we basically now formed NH4 plus, and you have OH minus. So in this case, you can see we basically have a Kc that leaves out water, because in this case, it's in excess. But in the previous case, it was not in excess, okay? So we can include it as part of your Kc as your, in terms of your equilibrium expression. All right. So, yeah, I can see who's writing this. It's this Chrissy. I can get a hold of you, and I'm going to now ban you for doing this on the screen. Can you please just stop doing this, because we know who you are. Okay. I'm sorry about the person that's actually writing on the screen, but it's coming up on my system and we will deal with them. The university does have a legal, we have some legal spyware that we can find people that are doing all of these. And I must apologize to those of you that want to listen and get good marks in your exams. But I know who that person is, and we will charge them. The university will get their legal team to charge them for doing this. Okay. So let them carry on, because with the for those that are being silly, you know, they don't want to listen. So we will deal with them appropriately. All right. So that's reactions in dilute aqueous solutions. So in your exams, it will say reactions in dilute aqueous solutions. So look out for some problems like these. Okay. This is what I wanted to show you, factors that influence equilibria. And I know many of you know this word, Le Chatelier's principle. Right? So remember when we have reactions, okay? And that means when a reaction is taking place. So you remember your teacher will say, according to Le Chatelier's principles, we need for the reaction to go in a forward direction. So you know now, you worked out the equilibrium constant K, you know, our K values. And if it was large, it went in the forward direction. If it was small, it didn't really go to completion, etc., etc. And if it was 1, it was at equilibrium. So you know how to do those calculations, right? If a system at equilibrium is subjected to stress, the system will react in a way that tends to relieve the stress. Now, stress means that, for example, if you have a reaction, right? If you put reactants together, and now the reactants are not reacting to give you the products. So what do you normally need to do to it? For it to have kinetic energy, we start heating up the solution, isn't that so? Then the molecules start to move, and basically they will collide and you would form your products. Now you're only forming products and products, and if you remove the products, then you're creating stress on the system because you got no more products forming, and then it will move to the forward direction. Okay, so 2 factors that cause equilibrium to shift is concentration and temperature. Okay, so remember this because you're going to be asked this question. Okay, and changing the amounts of products or reactants, so you can be changed either by changing the amount of a particular substance or the volume of the container. Okay, so change the volume causes a change in the pressure. So you know, if you increase the pressure, now I'll give you an example. Say if you got 2 gases, right? And I think your teacher would have told you this. If you had 2 gases as reactants and in a big room, right? Now it's very far for you to, for those gases to react. But just say, for example, you had a collapsible ceiling and you start now, you know, your piston, the piston kind of scenario. And if you start to compress the gas, that means you decrease the volume. So you're bringing the gases closer to each other, okay? And when you bring the gases closer to each other, they start to react, okay? So when you decrease the volume, that means you're increasing the pressure and then you causing the reactants to get closer. You see what I'm saying there, okay? So when you basically changing the amounts of products or reactants, adding or removing a reactant or product, the reaction shifts in the direction that will partially remove a substance that has been added or partially replace a substance that has been removed. Simply what we're saying here is, if you want the reaction to go in a forward direction, you'll remove the product. So as you remove the product, right, then the equilibrium will shift to account for the stress on the system that there's no product being formed. You see that? So adding or removing a reactant or product is what we're talking about. Okay, so here you can see in terms of CO and H2 forming methane gas and H2O. So if you remove the water, so you can see your original equilibrium, you got 0.613 moles of CO, you got 1,839 moles of hydrogen, and here you've got methane and you got water. So if you remove the water, okay, if you remove the water, the equilibrium shifts to the right. So now what happens is the forward direction, but the Kc does not change, okay? So you can see it'll shift to form more water. If you remove the water, okay, then you would now add more water stoichiometrically, right? So if you work out stoichiometry, you would add this. But your Kc, that means your equilibrium constant will not change, okay? So it will not change in terms of what you did. So can you see this was the original equilibrium? That means when you added CO and 3H2, when you're at equilibrium, this is what you have. But as soon as you remove the water, then your new equilibrium, because you only got certain so much of your CO that you have, and you can see it will now readjust itself to form more water. Can you see that? Okay, so just go through this, and it's so all you need to realize that the most important thing, if you remove product, you will form more product, and the reaction shift to the forward direction. Can you see? It moves to form more water. Okay, and the reverse will happen if you remove a reactant. That's all you have to know. Okay, so changing the volume, if you reduce the volume of a gaseous reaction mixture, shifts the equilibrium, whichever direction will, if possible, decrease the number of molecules of the gas. What that simply means is, if you're looking at CO gas, 3H2 gas forming methane and water, If reduce the volume at a constant temperature, the equilibrium shifts to the right, right? To decrease the moles of gas and reduce the pressure. So now that means you are you're reducing the volume. That means more CO2, more CO and 3H2 are reacting to move the reaction in the forward direction. Okay. So basically you decrease the moles of gas and you reduce the pressure. Okay. So basically that's reducing the volume at a constant temperature. Okay. If you increase the pressure, right? If you increase the pressure by decreasing the volume, right? So remember here, you reduce the volume at constant T. So in this case, if we increase the pressure by decreasing the volume, that means if we are decreasing the volume, you increase the pressure, and it will.
Hi, Ajay, please can you unmute?
Oh, sorry about that. Okay, let me just go back to the top then. Just.
No, it was only for a few seconds.
It was only for, I don't know how it just muted. Thank you. Sorry, guys, I'll just go back to Le Chatelier's principle. It's basically the two factors, it's concentration and temperature. Two factors cause the equilibrium to shift, right? So I spoke about changing the amounts of products or reactants. And here you just have to remember, if you take away the products, you will shift it to the forward reaction. If you take, and you can change the amount of the reactants, it will reverse the reaction. So all you got to remember in this case, if you remove a reactant or product, it will shift in either direction to account for that change. Okay, most of the times we in the lab, what we'd like to do is we want to increase the amount of product, so we remove the product and it moves in the forward direction. Okay, so I said, I think I did explain here where we showed at equilibrium, and then we remove the water and you can see the new equilibrium was established. Okay, so changing the volume, right? So reducing the volume of a gaseous reaction mixture shifts the equilibrium in whichever direction, right, will, if possible, decrease the number of molecules of gas. Okay, can you see? I'll read that slowly so that you understand that. Reducing the volume of a gaseous reaction mixture. So when we reduce the volume, okay, so that means you are making the volume smaller. The equilibrium in whichever direction will, if possible, decrease the number of molecules of gas. So what does that mean? So can you see here in this equation, CO plus 3H2 giving you methane. If you reduce the volume at constant temperature, the equilibrium shifts to the right. So if you reduce the volume, it shifts to the right, right? To decrease the moles of gas and reduce the pressure. Okay, so if you reduce the volume. If you increase the pressure, right? That means we can increase the pressure by decreasing the volume. You shift to the left, you can reverse the reaction, right? So in this case here, you can see CO2, if we increase the pressure, okay, by decreasing the volume, then the CO moves to the reverse, okay? If you decrease the volume and increase the pressure, it would move to the forward direction, because you can see the two reactants will start to react to go to the forward direction. Okay, so I hope you understand that. So if you increase the pressure, if you increase the pressure by decreasing the volume, it shifts to the left, the reverse reaction. So in this particular case, the CO will move to the left. Okay. So solids and liquids are incompressible and are not much affected by pressure changes. Okay. I just want to go through this again here. Yeah, you are reducing the volume. If you reduce the volume, the equilibrium shifts to the right. So you can see if we reduced the volume, that means we made the volume smaller, we move this to the forward reaction because the two reactants, okay, came closer to each other. And this to decrease the moles of gas and reduced the pressure. Okay, so it moved to the right. Okay, and in this case, if you increase the pressure, okay, when we increase the pressure by decreasing the volume, then it shifts to the left. So just find out in some of the examples that you have, and in the exams, they're going to ask you, what happens when you increase the pressure? What happens when you decrease the volume, etc., etc. Okay, so you can basically predict the direction of the reaction. So you can see in this case here, H2 and I2 does not respond to pressure changes. Okay, so this reaction is one of those reactions that does not react to pressure changes. Right, so changing the temperature, you all know, when you increase the temperature, it shifts an equilibrium in the direction that produces an endothermic change. That means which absorbs heat. Obviously, when you are heating something, you want to absorb heat. So if the reactants will absorb heat and go to the forward reaction, then so you can see in this case here, if you have an exothermic reaction, right? That means if A plus B, right, goes to C plus D, please listen to this carefully. If A plus B goes to C plus D and it gives off heat, right? If you increase the temperature, then it's going to go in the reverse reaction because it's already producing heat, right? If you have an endothermic reaction, so if reactants A plus B takes in heat, and if you add heat, you can see it will move the reaction to the forward direction. So mostly reactions that are endothermic, that absorbs heat, you will apply heat to. I think this is a very straightforward understanding of that. Okay. So K changes with temperature. If that means your equilibrium constant. Now you know why. If you're going to add more products, if it's going the forward reaction, then you know that your K will become, right? So if the forward reaction in an equilibrium is exothermic, raising the temperature, it causes the equilibrium constant to become smaller, right? That means if I look at here, if you're going to heat the reaction, if you have an exothermic reaction, if you heat it, it's going to now form more reactants. So remember, K is equal to C to the power C times D to the power D all over A to the power A and B to the power B. And if the denominator is increasing, K becomes smaller. I know you understand that, and that's what they're going to ask you. For an endothermic reaction, if you're going to heat up the reaction, you're getting more products. So K is equal to C to the power C times D to the power D all over A times B. Because C and D increased and A and B decreased, K will increase. Okay, so that's how I want you to remember this chemical equilibrium. Okay, and it's quite easy to understand that. Agents that do not affect the position of an equilibrium is your catalyst. Okay, so you know we add catalysts and they basically will mostly not be consumed, and they basically speeden up the reaction. So I'm not going to go too much about catalyst. I think you know about that. In the rest of these notes, you basically have examples. I want you to go through them. They're very, very easy examples. If you go through my examples, I can guarantee you, you will get all of these problems right when it comes to chemical equilibrium. Okay, so I'm going to stop there for now. Right, so now I'm going to basically just quickly go to, I'm going to give you a 5-minute break. So according to my particular time, it's 1:58. So we're going to start again at 2:05. And my next section is also a very important section. So don't go away, guys, because I'm going to do acids and bases. I'm going to show you how to do all the calculations. And I'm going to try and go through it quickly. And thereafter, I'm going to do electrochem. You also have to listen to the electrochem because I'm going to show you all the quick methods and how to get. So these 3 sections will earn you really good marks for your matric exams, right? So again, I just want to reiterate, go through the fundamental basics, understand what it means. The questions are so easy and you will get it right. Okay, so at 2:05, I'm going to start off the acids and bases. and I'm going to show you how easy it is to understand acids and bases. And I'll show you the calculations, and then you can do as many examples as you want to. Okay, so you can take a 5-minute break, maybe get a quick bite and something to drink, and then I will start off at 2:05. And at the end of the session, I will. So some of you are also giving us questions. I do understand that. I'm going to take cognizance of that, and I will answer those questions that you're asking, because we have an online email support. So for now, I want to get the fundamental information to you so that you understand. I think it's more important. Okay, so it's more important for you to understand basically the content. So now you see chemical equilibrium, you understand how it's done, how the calculations are done, what it means, increasing volume, decreasing volume, catalyst, the temperature changes, concentration changes. You cannot go wrong with this section. Okay, I'll see you in 5 minutes. Okay, is everybody back? Can I just get some thumbs up to say that you're back and you all can hear me? Okay, thank you. Right, let's get it go on. Right, acids and bases, right? So, you know, understanding acids and bases can be very confusing, but at the same time, I'm going to try and give you a very logical understanding of acids and bases. So you all know that if I ask you to give me, name me one acid, then most of you will talk about acetic acid, which is vinegar, right? CH3COOH. So, and you know, the one thing that really irritates me is when you go to Kentucky or you go to McDonald's, or they give you those vinegar sachets to put on your burgers, and you know, whenever you buy takeout and stuff like that for your French fries or your potato chips that you have, so acetic acid is used in that particular for that use. So if you live in Durban, acetic acid is actually made by an anaerobic process, and they use an acetobacter. So if you go down Springfield Park across Macro, there's a huge industry called NCP Chemicals, and they used to basically take molasses, which is a byproduct of the sugarcane industry, and they used to add an acetobacter, and basically they used to carry out an anaerobic process without oxygen, and that used to now make vinegar from a fermentation process. So the acetobacter used to ferment the molasses and will make vinegar. If you added oxygen to it, then you would form ethanol, and you would get ethanol. That's their main product that they make. So you see, if you have oxygen, and if you don't have oxygen, you can make two different products, and that's what NCP does. The CO2 that they make, carbon dioxide. So what you do is, if you take the carbon dioxide and if you compress it, so if you decrease the pressure and you squeeze the carbon dioxide molecules together, guess what you get? You get dry ice. Okay, so they across there you'll see there's Afrox, and Afrox buys the dry ice from them. And another product they get is methane gas, because methane gas comes from the fermentation process, and they sell that methane gas to companies, to Afrox as well, to fill, to use as gas in byproduct, to use as gas in some of your canisters and stuff like that. Some of the methane gas is piped to Sasol and to many industries. So you see, nothing is wasted in industry, right? So this acid, you know that our common acids, wherever you see an acid, you see an H. So you remember there's the Bronsted-Lowry theory, Bronsted acid and a Bronsted base. So we say a Bronsted acid is one that donates a proton. So in HCl, if you're donating an H+, then it's basically an acid. And if you have an OH group, we call that the base. But you also know that we have bases like carbonates, calcium carbonate, sodium carbonate, lithium carbonate, potassium carbonate. They're also called bases, okay? So an acid is by virtue of having a hydrogen, H+, and a base by virtue of having a hydroxyl. This is called a hydroxyl group, okay? So for your understanding, simply an acid is a proton donor, or it's got H, okay? So HCl, HNO3, CH3COOH, etc., etc. So you know the properties of acids. It has a sour taste, it turns blue litmus red, and it neutralizes bases, okay? And bases, on the other hand, is very soapy, it's bitter, and it turns red litmus blue. Now, I know everybody gets confused when you say, what does a base turn, red litmus blue or blue litmus red? And everybody gets confused, right? So just remember, an acid turns blue litmus red and a base turns red litmus blue. So and it neutralizes acids. Right, so that's that. Then we have what we call an areneous acid, right? So an areneous acid is a substance that when dissolved in water, increases the concentration of hydronium ions. So what is this hydronium ion? It's basically H2O plus H plus gives you H3O plus, and we call this a hydronium ion. And so when we talk about an areneous acid, it is a substance that when you add it to water will basically form H3O plus. So in other words, it is a proton donor as far as that is concerned. Okay. And an areneous base is a substance that when dissolved in water, increases the concentration of the hydroxide ions, OH minus. These are things that you know, okay? But I'm just now refreshing your memory about that. So you can see the hydronium ion is basically, there's our H plus coming from the acid, and simply it adds to water, and you can see there's the H3O plus, right? It's called the hydronium. So when we write H plus aqueous or just, we understand that it's hydrated. So that means we don't write it as H3O plus like that you see there. Right, so let's do common acids. HCl is a monoprotic acid. That means it only has one proton, but sulfuric acid can have two protons, so it can give it off twice, okay? But sulfuric acid will give off the first proton. That means when you add water, it dissociates, right? So you see when we're adding water here, that means it pulls off the proton. Or we talk about dissociation. Dissociation, you must have heard of the term, okay? And so all of these, when you add them to water, they will give off their protons. So there's acetic acid, CH3COOH. And polar covalent molecules in a pure anhydrous state, okay? That means, what does this mean? These are polar covalent molecules in the pure anhydrous state. So when water, when you dissolve it in water, can you see the HCl completely dissociates into Cl minus, and the H goes to the H2O. Now remember, the chlorine has got a very high electronegativity and it pulls electrons towards itself. So we call it a polar molecule because it's got a Cl minus and an H plus. It's like the polar regions, okay? So we call them a polar covalent molecule. That means they have this separation of charge. That's what polar covalent molecules mean. But when HCl completely dissociates, there's no molecular HCl. That's why we call it a strong acid, okay? You cannot just look at an acid and say when it is strong. You can only say if it's strong if it completely dissociates. That means it gives off all the H pluses. So the more H pluses an acid gives off, the better it is. Right. Now, if you take a non-metal oxide and if you add it to water, so this is like the anhydrous form of sulfuric acid. See what has happened here. And you remember this from the contact process, right? Oh, this is a terrible reaction, by the way, because it's so violent and so hot. You actually form a mist of sulfuric acid, right? So this reaction here in the contact process is very violent. They actually don't use this reaction, by the way. So this is sulfur trioxide, and we call it a covalent oxide, or we call it an acidic oxide. And when you add it to water, can you see it's reformed the acid? So what does it mean? It means if I dehydrate, if I take out water from sulfuric acid, it'll form SO3 and H2O. See that? So non-metal oxides as acids, right? That means if you take a non-metal oxide from the covalent, so NO2, NO, those are called non-metal oxides, right? So like if you take NO3 and NO2 and add it to water, you'll get HNO3. Okay. Let's look here, H2SO4. HNO3. If you remove H2O from here, you'll form NO2 and NO plus H2O. Okay, so let's look at bases, ionic compounds that contain OH or O2 minus. So you can see here, again, you call this a strong base because if you add water to sodium hydroxide, it will completely dissociate into Na plus and OH minus. That means you won't have molecular NaOH. So that's why we call it a strong base. And again, if you take the metal oxide, the reason why we're calling it a metal oxide, because it comes from either group 1 or group 2. So you remember group 1 are the alkali metals and group 2 are the alkaline earth metals. So group 1, group 2, and group 3 on the periodic table are metals. But if you go from group 4, group 5, group 6, those are called non-metals. Okay. So you can see if you add calcium oxide to water, you form calcium hydroxide. And this calcium oxide is basically lime. Okay. So when you add water to lime, we call it slaked lime, right? So this is lime water, calcium hydroxide. And you remember when you bubble CO2 into lime water, it turned murky because you formed calcium carbonate. See how all of these things are sort of related to each other. You can see that. Okay. So that's why I said chemistry is interesting when you understand what's going on here. And then you have what we call molecular bases. So ammonia is a molecular base. Now, let me tell you about this here. When we buy ammonia, when we buy ammonia, it's ammonia in its pure state is a gas. It's a gas. This is not right. This NH3 plus H2O, it's supposed to be an equilibrium sign, by the way, here. Because this is not supposed to have a forward reaction sign. It's supposed to be an equilibrium sign. Because a solution of ammonia is in equilibrium with the gas and NH4. So when you buy ammonia, it's in an NH4OH. That's the solution that you buy, not NH3, because NH3 in its pure form, it's a gas. Okay. So strong acids and weak acids and bases. So like I told you, a strong acid or a base is one that completely ionizes or dissociates. They are also considered strong electrolytes. Now here they are: HCl, H2SO4, HNO3, HI, HBr. That means when you add water to all of these, you will form H3O plus Cl minus. In this case, you'll form HSO4 minus plus H2O. The second dissociation is not very prominent. Here you'll form NO3 minus plus H2O, Br minus plus H2O, I minus plus H2O, ClO4 minus plus H2O, BrO4 minus plus H3O plus, sorry, H3O plus, H3O plus. Okay, that means all of them will dissociate. But acetic acid is a weak acid. It doesn't like to form CH3COO minus plus H3O plus. That means it's very mean in giving off this proton, right? So it's a weak acid. And that means it has a Ka value. Now I'm talking about equilibrium acid and acid dissociation constant K, right? It's ringing a bell now. I'm going to explain that to you just now. So can you see a weak acid or base is one that only partially ionizes? That means if you take acetic acid and drop it into water, you're going to get CH3COOH, a lot of it. That's why we use it in our vinegar and stuff like that. Okay. It doesn't give off a lot of H plus. All right. And the reason for that is as soon as it forms CH3COO minus, the conjugate base, right, is a strong base. So it grabs the proton again and moves in the reverse direction. Right. So weak acids or bases is one that partially ionizes, and strong bases contains OH, which is a strong electrolyte, and a weak base typically contains nitrogen, right? So strong bases like sodium hydroxide. So now you know what are strong acids and what are strong bases. So when it completely ionizes, it's a strong acid or a strong base. That means there'll be no molecular HCl, no molecular NaOH. It completely breaks up into two. Okay, so you know that. Here, I'm not going to go through this. You can go through the examples. I want to go, but the solutions are here. You can see BaO plus water, and you can form, so you can see H2S plus H2SO4 giving you H3O plus H minus. So it's an acid because it got the H plus. So immediately you can see the base because it's forming OH minus. These are quite straightforward, right? Then we have the Bronsted-Lowry which is the ones that we are used to. Bronsted-Lowry acid is a proton donor. Bronsted-Lowry base is a proton acceptor. Okay, so here, can you see? We're calling according to the Bronsted HCl. Here, it's an acid because it gave off H+. Now, when it gives off the H+, it's an acid, right? It's a strong acid. Why? Because as soon as you add water to it, you no more have any more HCl forming. But remember, acetic acid will not give off all the H+, so it's a weak acid. Then the Cl- becomes the base. See? So those two become a conjugate acid-base pair, conjugate base. And because the H3O plus took on the proton, it becomes an acid, and that becomes a conjugate pair as well. So you got two conjugate acid-base pairs. Okay. And it's quite easy for you to understand that. So the base is the same. Can you see? Ammonia now takes a H plus from the water and it forms OH minus. So that's why we call it a base, right? So you can see in this case, NH3, right, took on an H plus and becomes NH4 plus. And because this can now give off H plus, it becomes an acid. So that's a conjugate acid-base pair, and that's a conjugate acid-base pair. Just go through it and you'll see it's quite easy to understand this, right? So conjugate pairs, for conjugate acid-base pairs, the stronger the acid, the weaker is its conjugate base. So if you look at here, for HCl, if you have a strong acid, the conjugate base is weak, okay? It's a weak conjugate base. Right, now, example, formic acid is a stronger acid than acetic acid. Which of the following is the stronger base? CHO2 minus or CH3OO minus? That's quite easy. Remember we said the formic acid is a stronger acid. The stronger the acid, the weaker is the conjugate base pair. Okay, so I think you'll be able to answer that. And acid and base strengths. Now listen to this. If any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So can you see here? Can you see what has happened here? That HCl, right, moved to H2O. So H2O is a stronger base than Cl minus because it grabbed the proton from there. So it's making it a base, isn't that so? To grab the proton. So that the equilibrium lies far to the right, that K cannot be measured, right? Here you can see, now if you're going to talk about K. So if you have to write out K and acid dissociation, it's actually undefined because if I write out K is equal to H3O plus times Cl minus over HCl plus H2O, but there's no more HCl, so HCl is equal to 0. So K, the acid dissociation constant K, is equal to concentration of H3O plus times Cl minus all over HCl times H2O, but there's no ClO, so HCl is 0. So that's going to be K is equal to the concentration of H3O plus times Cl minus over 0, so it's undefined. Okay. I'm not too sure if you know what's an amphoteric substance. An amphoteric substance is one that can act as an acid or a base. So you can just go through this in terms of your theory. I want to go through the examples, okay? You can also go through these examples on Bronsted-Lowry acids or bases. Right, let's talk about the ionization of water because this is important for you to understand going towards calculation of pH, right? So when you take the ionization of water, can you see H2O breaks up into H plus and OH minus. But strictly speaking, the hydrogen ions exist in water as the hydronium ion, H3O plus. So the dissociation of water should therefore really be written as H2O plus H2O. Can you see that? So that means H2O plus H2O gives you H3O plus OH minus. That means so instead of saying 2H2O, you can just say H2O plus H2O will give you H3O plus OH minus. So we call it the autoprotolysis. And if you write an equilibrium constant, there we go. It's going to be H plus, actually it's H3O plus, but we're writing it as H plus over OH minus over H2O all squared, okay? And since the water is only slightly ionized, the molar concentration of water has essentially a constant value of 55.6 moles per dm cubed, okay? Therefore, the term H2O squared, H2O raised to the power 2 is a constant which we can combine with Kc. So in other words, can you see here, this H2O raised to the power 2, okay, is a constant, okay? So therefore, we can rope it in with Kc, so we call it Kw, and that's how we call it the ionic product of water. So you must have come across Kw is equal to H plus OH minus. Okay, and obviously Kw varies with temperature and its value is known. So it's 1,00 times 10 to the minus 14. Okay, so if you take pure water, okay, and if you want to find the concentration of H plus or OH minus, you simply take the square root of Kw, right? And that is equal to the square root of 1,00 times 10 to the minus 14, and we get 10 to the minus 7 molar, okay? So see here, we're saying that Kw is equal to H plus OH minus, and H plus OH times OH minus is equal to 1,00 times 10 to the minus 14. So we can simply, that times that, because H plus is equal to OH minus, we can say H plus all squared is equal to, so here, because in pure water, H plus is equal to OH minus, right? You can either write it as H plus raised to the power 2 is equal to Kw, and that is equal to the square root of Kw. I think you know that, okay? Right, so a solution in which H plus is equal to OH minus is a neutral solution, all right? And let's move on. If H plus is greater than 10 to the minus 7 molar, the solution is acidic. If H plus is less than 10 to the minus 7 moles, it's basic. Right, now, let's look at some questions, and this is what you want to know. So please pay attention, right? pH, pOH, and pKw. So pH is simply the minus log of the hydronium ion concentration raised to the base 10. And the pOH is equal to minus log of the OH concentration to the base 10. So if you know H plus concentration, it's minus log. So if it's 0.1 molar, that's minus into minus 1, if you got your calculators. If H plus is 0.1 molar, that's 1 times 10 to the minus 1. So that's minus into minus 1, your pH will be 1, right? So you can see pH, pOH is simply the minus log. It's a mathematical calculation, okay? And here pOH is also a mathematical calculation. So you know Kw is equal to H plus times OH minus. If you take the logs of it, that's minus log Kw is equal to minus log H plus minus log OH. Remember this because they will ask you questions on this. So minus log Kw is pKw. So you can see here, minus log H plus is pH, and obviously minus log OH. So that's going to be plus pOH. So plus into minus log OH, right? So because you got minus, we multiply all across by minus. So pKw is equal to pH plus pOH. All you got to remember is this, and Kw is equal to H plus OH minus. And you got to remember pH is equal to minus log, and I'm going to show you some examples now, right? Okay, so pKw will always have a value of 14 because it's pH plus pOH. In a neutral solution, you know the pH is 7, which is equal to pOH. In an acidic solution, the pH is less than 7. In an alkaline or basic solution, the pH is greater than 7. So if pH is less than 7, pOH has to be greater than 7. And if pH is greater than 7 in an alkaline solution, pOH has to be less than 7, right? Just if you're a bit confused, just remember that. Now, pay attention to this example. right? Because this is what you're going to be asked to calculate. Find the pH of a solution for which H plus is equal to 4 times 10 to the minus 5 moles per dm cubed. Please use your calculators, and it's very simple. As you remember, pH is equal to minus log of H plus. So it's minus log of 4,00 times 10 to the minus 5. It's going to be, remember, the minus into a minus, because log of 4 times 10 to the minus 5 is minus 4,398. So a minus times a minus gives you a plus value. Can you see that? So your pH is about 4.4. Okay. Straightforward calculation of pH, right? Now, listen to this. If you've got the pH and you need to calculate the H plus, it's simply using inverse logs, right? So if I gave you the pH, remember pH is equal to minus log of H plus, which is equal to 5,643. In this example, here, we gave you the H plus. In the next example, we gave you the pH. So that is equal, so log H is equal to, actually it should be minus log H is equal to 5,643. So because we get rid of the minus, log H is equal to minus 5,643. So all to get rid of the log, you'll simply say H plus is equal to 10 to the raised to the minus 5,643. It's so easy. So if you ever get a pH value and you want the H plus, simply say 10 to that minus 5,643. Can you see that? And on your calculator, you will get that value. But I can tell you in your exams, if you simply say H plus is equal to 10 to the minus 643, you will get marked right because it's the right answer. That means you just have to put that in your calculators. You see that? So if you got the H plus concentration, you can calculate the pH. The same will work for OH. If you got the OH concentration, you can calculate the POH. Here, if they give you the pH, you can calculate the H plus. If you got the POH, you can calculate the OH minus. Okay, so let's have a look at that. Now, this is an important, the acid dissociation constant, Ka, or say K subscript A. Now, remember, we only evaluate or write the acid dissociation constants for weak acids, because strong acids completely dissociate. You cannot have well, actually, if an acid like HCl, the Ka is undefined, or it's very, very large as such, right? But generally, you will work out Ka or acid dissociation constants for weak acids. Right, so here's a weak acid HA dissociating in water to give you the H3O plus, okay, plus A minus, right? So now what we did is we leave out the water. So remember, this is only for acids and bases. Earlier on, I did equilibrium constants. There, I told you when the water was limited, you would add it to the equilibrium expression. And if water was in excess, then you eliminate it from the equilibrium expression. But for pHs, you do not take water into consideration for your Ka. So that's why we wrote it as HA aqueous, going to produce H plus and A minus, which is the conjugate base. So can you see, there's the dissociation constant, right? Which is H plus. So again, it's simple. It's simply the product. It's the sum, not the sum, sorry. It's the multiplication of H plus over HA, right? And now we got the, so again, if you have a high amount of products, H plus and A minus, you'll have a high Ka, which means it's a strong acid. That means it's dissociated and moved in the forward direction. If you have a low Ka value, that means the denominator is high, and that means the numerator is low, which means the HA did not go in the forward direction. I'll say that again, and I'm going to say that slowly. If you have a high Ka value, that means H plus and A minus are high. Can you see that? The numerator will be high. That means the HA is low. That means all the HA has dissociated in the forward direction to form H3O plus and the conjugate base. If your acid dissociation constant value is low, it means you got a high HA value, and you got low H plus and low A minus, which means the weak acid does not dissociate to form HCO plus plus A minus. Okay, that's important. There, what I'm saying. The larger the value of Ka, the stronger is the acid. That means it's forming more H plus ions, which, and you know, pH is minus log of the H plus. Okay, so you can even find pKa, which is equal to minus log of the Ka. Okay, so that's just one of the calculations that you can use. So the same is seen with the bases, right? Exactly the same as the acids. So if you got a base, you're going to form Kb. So instead of acid, it's Ka. For base, it's Kb. And here, there's the base that now takes an H plus to form the conjugate acid. And there's your base. So remember, we're forming the OH minus. So Kb is equal to BH plus plus OH. Remember, I said water is not part of the Kb expression. And you would now have a base ionization constant. So you have an acid dissociation constant, and you have a base dissociation or base ionization constant, because the base has also dissociated in water. Okay, so pK, so the larger the value of Kb, the stronger is the base. Okay, so you know that. Right, now, you've done titrations and you've done neutralizations, right? So here's a typical neutralization reaction. HCl being neutralized by sodium hydroxide. So if you've got 100 cubic centimeters or 100 moles, 1 cubic centimeter is 1 mole, so 100 cubic centimeters is 100 moles of a 0.1 molar or a 0.1, sorry, this is 1 moles per dm cubed or 1 molar HCl, and you add 1 mole of NaOH to it, right? So you neutralize, can you see? You're basically going to neutralize the acid. So you're adding 1 molar NaOH to 100 moles. So the equivalence point occurs when exactly 100 moles of base, of 1 molar base, has neutralized all the acid to form a salt, a neutral salt, and water, right? So we call that the equivalence point. And when you do a titration, you would use an indicator, and we call that the end point. Okay, so you can see the pH at the start, right? So if you got HCl, it completely forms H plus and Cl minus. So your pH is going to be minus log of the H plus. And what's your molar concentration? 1 moles per dm cubed. Can you see that? So it's going to be minus log into 1, and the pH is 0. Yes, you can get a pH of 0. You can even get a pH of -1. It's just a numerical value. Okay, so if try this out, find the pH of a 10 molar HCl solution. So minus log of 10, you'll get a -1. So you can see you can even get a pH of -1, meaning it's very, very, very acidic. Okay, so now you know how to calculate pHs. So pH before the equivalence point, determined by amount of acid not yet reacted with the base. So, for example, I want to take this example here. You started with 100 moles of 1 molar HCl. So there I've got my HCl, right? I've got 100 moles of it. What if I added 50 moles of NaOH, right? So I got 100 moles of HCl, 1 molar, but I only added 50 moles of 1 molar base. Now, obviously, you can see that you're going to have HCl remaining because only 50 moles of sodium hydroxide was added. So that means only half the concentration of HCl was neutralized. So we call that before the equivalence point, right? So if 50 moles of NaOH was added, your total moles was 1 moles per dm cubed times, so we had 1 molar, and because we have 100 moles, we have to convert it to dm cubed. So 100 moles is 0.1 dm cubed or 0.1 liter, right? And we get 0.1 mole. So molarity times volume in dm cubed gives you the number of moles. Can you see that? So you're going to get a problem like this. So you can say initially amount of HCl or total moles of HCl. Can you see how much we gave it to you here? It says start with 100 moles of a 1 molar HCl. And we are saying now at the start, we got 100 moles, which is 0.1 dm cubed of 1 molar HCl. You happy with that? And molarity times volume in dm cubed, the dm cubed and the dm cubed cancels and we get moles. So how much of NaOH was added? So we added 1 moles per dm cubed, and remember we had 50 moles. Yeah, we're saying 50 moles. So 50 divided by 1,000 gives you 0.05 dm cubed. To convert cm cubed to dm cubed, you simply divide by 1,000. 50 cm cubed is the same as 50 milliliters. Okay, so that's why we got 0.05. Now that works out to be 0.05 moles. So all the OH was neutralized by the HCl, but we will have 0.1 minus 0.05. That means that 0.05 moles of H plus is unreacted or still remaining. So because you've took 100 moles of HCl and you've added 50 moles of OH, so all the OH would have neutralized. But remember, your new total volume is 150 moles. So the H plus remaining is equal to 0.05 because I subtracted the amount of HCl that I took initially. I added OH, it reacted with 0.05 moles. So 0.1 minus 0.5 gave me 0.05 moles of H plus that's still remaining. And that 0.05 over the new total volume gives me 0.0333 molar of the H plus, right? So now if I calculate the pH, it's going to be minus log of the H plus, which is equal to minus log of 0.33, and your pH is 0.477. So when you're doing a titration, they will give you the amount of acid added. They will ask you the amount of base added. Then you will find how much of unreacted acid there was and take the total volume. So by difference, you'll get the amount of acid that's remaining. You put that over the total amount of, remember to convert to dm cubed, okay? And you can work out the molarity of the unreacted acid. Okay, so if you use my example like this, and you can do all other examples that you have, you can find the pH of your solutions in the calculations, right? So you see, you are able to do this in the structured way. So please do it like this, okay? Then look at the pH at the equivalence point. It's going to be 7 because you got no H plus. That means you got only NaCl and water. So from this equation here, right, you only got water, and so nothing is going to give you. And obviously the pH is coming from the square root of 1 times. Mebloshan, I can see you doing all the stupid things with your arrows. I'm going to also block you from this. Please stop doing that. I'm taking your names down and I'm going to tell your parents what you've been doing, and the university is going to deal with you legally. I'm telling you that. So you can see from this, you're only getting pH coming from the dissociation of water. And you remember earlier on, I told you, if you get the square root of 1 times 10 to the minus 14, because you're only getting the dissociation of water. Here, I'm going to go through this here. See, OH, where was it? Here. Here. In pure water, H plus is equal to OH minus. and it's 10 to the minus 7. So minus log of 10 to the minus 7 is minus into minus 7, and you get a pH of 7. So at the equivalence point here, right? So at the equivalence point, okay? So before the equivalence point, it's going to be acidic, right? At the equivalence point, you're getting the square root of 1 times 10 to the minus 14, which is equal to 10 to the minus 7, and minus log of minus 7 gives you 7, right? So that's how we get a pH of 7. After the equivalence point, so imagine you added 150 moles of NaOH to 100 moles, right, of HCl. So now you're obviously going to have more base left. Can you see? So that means excess volume of NaOH added is 150 minus 100 moles of base. So you're going to have excess base. Okay. So like we worked out in the acid here. So total moles of HCl was 1 molar times, but if you added now 150 moles of base, then you're going to have OH minus remaining after the equivalence point, right? So after the equivalence point, you can still do it. You can still do it like this. You can have total moles is 1 molar times 0.1 moles of OH added is going to be 1 molar times. This will be now 1.5 because you got 150 moles. Sorry, 0.15 dm cubed. But then you're going to have, instead of having 0.5 HCl, you're going to have 0.05 moles of base remaining. So this is after the equivalence point. Okay. So can you see that excess volume of base was 50 moles, and 1 times, so you worked out the excess base that was remaining, and you can find the pOH. So minus log, but remember pH, when you want to find the pH, if you know the pOH is going to be 14 minus pOH, and you can get the pH. So use this example, and this is definitely going to help you in terms of titrations and calculating pH. Okay, so I'm going to stop there now with pH. You can go through the rest of the notes because it explains calculations and calculating Ka from the pH. I think I'm just going to go through the calculation of Ka from the pH, and then I'll move over to electrochemistry. Okay, so calculating Ka from the pH. Okay, let's look at this example. The pH of a 0.1 molar solution of formic acid at 25 degrees is 2,38. Calculate the Ka for formic acid at this temperature. So when you are given the pH, you can calculate the acid dissociation constants. Now you know these examples because your teachers have done them with you. So just go through this example, and the way I've set it out will help you in your calculations. Okay, so now you can see here, if you look at the solution, right? Formic acid is a weak acid, right? So if you simply take pH, which is minus log of 2,38, you're going to get the H plus concentration, right? So H plus is equal to 10 to the minus 2, which is equal to 4,2 times 10 to the minus 3 moles per dm cubed. And then if you got H plus, we assume that the HCO minus will be the same. So you got H plus and HCOO minus, okay? So then you can see you got, initially you got the formic acid, then you got the H plus, and you got that. So if you had a 0.1 molar, you know how much of formic acid you formed, and you know how much of H plus, and you know how much of that. So at equilibrium, you simply have Ka is equal to H plus over the conjugate base and your HCO. So all you do is simply now substitute these values. So at equilibrium, you know that the formic acid is going to be 0.1 minus 4,2 times 10 to the minus 3, right? But look at this value here. It doesn't change a lot, right? It doesn't change a lot. So in most of the cases, we leave it as 0.1, but you can calculate the Ka by simply knowing the pH of a solution. So if you had the pH of a 0.1 molar solution of formic acid, right? So you can see how we calculate the H plus, which is minus log of the H plus. Then you've got H plus, you got the HCOO minus. You write, I know somebody initially said the Rice method. Yeah, you can see where you got the Rice method. It's reactants, initial, change, and equilibrium, right? So initially you had 0.1 molar. The change was 4,2 times 10 to the minus 3 because we calculated it from here. And so you can see the change in all. So it's 0.1 minus that. And once you get that, you'd simply substitution. So it's a straightforward. Okay. And we talk about percentage ionization. You can have a look of that and then see the example that I've done, which so go through these notes and it'll show you how to calculate Ka, etc., etc. All right. And we can also calculate pHs for weak bases as well. But the titration one that I showed you is a definite must for your exams and those types of questions. Right. Geez, the time is really flying away. I want to quickly switch. I'm going to share my next slide on electrochem, redox reactions and electrochem. Ashwin, if you're still on the chat, can I possibly go past 3 o'clock?
Yeah, I think that's fine. The students are willing to stay, they can stay, and if you have the time, you can continue.
Okay, guys, you have to stay for the electrochem because you can score your marks there. I promise you. And I'm going to show you some very, very quick methods. And I'm going to give you a very clear understanding of electrochemistry because I know many of you battle with that. Electrochemistry is actually something that you have to go through. Okay, so I'll give you a 5-minute break, right? And then I'm going to start the electrochem. Right. So for the acids and bases, I'm just recapping quickly, right? For the acids and bases, just remember how to calculate pH, how to calculate POH, the titrations, initial before the equivalence point, at the equivalence point, after the equivalence point, then how to calculate the Ka from pH, okay? Go through those. Those are the 3 main aspects of these things. I've laid it out very nicely in my notes. If you go through my notes and do all those calculations, you will
Okay, did we lose Ajay? He's not.
I think he's just away from his mic, Ashwin.
Okay, I think he did call for a small break, right? Let's just give him a few seconds to get back on. Okay, in the meantime, students, I'm going to get my computer guys to post the notes up on the website that I've been putting on. So just it's the weekend, so we need to get staff to do it. So it's going to be a bit difficult, but it may be up tomorrow or Monday. Just keep an eye out on the website for it. Hi, Ajay, are you back? Okay, I think Ajay is having a problem with his connection. So what we can do is we can take the 5 minute break that he spoke about, and maybe we can come back in 4 to 5 minutes. Okay, it'll give him some time to sort his connection out. Please stay logged on. Do what you need to do, and then but don't log off. Okay, thank you. This is the joys of online. This is normal.
Okay, I'm back. Sorry, guys. There's been some glitches on my side with the online. Right, I'm going to kick off now, and I want you to pay attention. I'm going to try and speak much slower, but I think if you're following, I'm going to start off with rules for assigning oxidation numbers.
Ajay,
Hi there.
sorry to disturb. I just gave them a few minutes break.
Oh,
So
you
I'll
did? Okay.
come back at 4 minutes past.
Okay,
So about
cool. All right.
3 minutes more. Thank you.
Okay, so we'll start at 5 past. That's fine. Okay, all right, cool. Okay, guys, let's get a move on. Right, so before we start with electrochemistry, you need to understand oxidation numbers, because when we look at electrochemistry, there's change in oxidation numbers. There's a redox reaction that takes place. So there's oxidation and there's reduction. So I'm going to, you will have access to these notes, but I think in your textbooks and in your notes, you have rules for assigning oxidation numbers. If you just go quickly through these rules, in free elements, that means when you see H2, Br2, Na, so in things in their natural states, they have zero oxidation numbers, right? So for example, all the metal ions as solids have zero oxidation numbers, Fe, for example. So for ions composed of one atom that is monoatomic, the oxidation number equals the charge on the ion. So if you have lithium solid getting oxidized, it goes to Li plus. So the oxidation number on Li is +1, right? So barium, if it gets oxidized, so it goes to +2. Iron, if it gives off 3 electrons, it goes to +3. So if you get reduction, so I minus is -1. In oxygen or the oxide molecule, we have the oxidation number as -2. You've got to know these things. Then you can identify what happens in terms of oxidation, changes in oxidation numbers. So oxidation is the loss of electrons. And if something gets oxidized or a species gets oxidized, it becomes positively charged. If a species undergoes reduction, and it becomes negatively charged. So you know all the halogens, Cl minus, Br minus, I minus, all of these like to be negatively charged, right? The oxidation of oxygen in most examples, so when you see MgO, even in water, is called the oxide, right? It's a -2, it's the oxide, okay? But in peroxide, and you can see it's a O22 minus, and the oxidation number is -1. It's a special case, okay? There are some exceptions, like in hydrides. You can see that the oxidation state of hydrogen is -1. Now, you always know hydrogen is +1, but in this case, because lithium is +1, hydrogen is -1, and so forth. In also, if you look at hypochlorite, JIC, OCl minus, the overall oxidation state of this is -1. So in the first case, oxygen is -2. So the chlorine atom here is -1. Sorry, +1. Okay, I'm going to say that again. So we have what we call oxo anions. So OCl minus is hypochlorite and hypobromite, right? So hypochlorite and hypobromide, hypochloride and hypobromide, okay? So in this case, you can see that oxygen is -2, and for the whole molecule to be -1, the chlorine atom has to be +1. And here, the bromide ion is +1 and oxygen is -2. So this whole OCl minus is referred to as hypochlorite. Hypochlorite as in sodium hypochlorite, and you know it as JIC. Okay, it's the active ingredient, and hypobromite as in OBr minus. Okay, so I'm just showing you how to get the oxidation numbers. And here's an interesting one. Oxygen can be called a superoxide. So O subscript 2 and the O minus, superscript minus, is called a superoxide. So each oxygen is -1/2, but because it's a dimer, it has an overall charge of -1. Okay, that's just an example of that. So all I wanted to show you was oxidation numbers and how you should be going and understanding oxidation numbers. So I'm just going to share now with electrochemistry. Okay, so in electrochemistry, it's the study of the relationship between chemical change and electrical energy. So you know a chemical reaction which involves an oxidation and a reduction. That's why I told you know your change in oxidation numbers is basically going to, it's also called a redox reaction. and we're going to produce an electrical energy. So I'm just going to show you how to understand to do this calculation and what to and how to do the calculations. Okay, so you can read up about electrochemistry. I'm going to go straight to oxidation reduction. Remember, oxidation is the loss of electrons, reduction is the gain of electrons, right? So let's look at an example. Here you can see this is a redox reaction, right? What is being oxidized and what is being reduced in the following redox equation. Now, obviously, you have to know the oxidation number. So there, CD, solid, you can see immediately that's going to be a 0. So above that, you put 0, right? Here, you can see in nickel oxide, oxygen is -2. So because you got 2 oxygens, that's -4, right? And the nickel should be +4, right? The nickel should be +4, and here the O2 should be -4. You really don't worry about the water. So obviously you can see immediately that you got OH, which is minus, that's -2, and you got cadmium, that's +2. So cadmium obviously got oxidized, okay? So CD0 and CD2 plus, so you can see that's the oxidation. And if you take here, okay, Ni is going to be +2 because you got OH minus and OH minus, that's -2. And here you got Ni, that's +4. So Ni +4 went to Ni +2, so that became reduced. So you can see how these oxidation numbers and the changes in the oxidation numbers. So that's what I'm saying to you in terms of a redox reaction, right? Now, let's look at electrochemical cells. This is where you want to know how to understand electrochemical cells, because this is where they're going to ask you to do calculations, right? So so you know what is a voltaic cell or a galvanic cell. In a and you're going to be asked to do a calculation based on a voltaic cell, coming from the word voltage, and galvanic cell. Or it was just named after this guy, Alessandro Galvani. He was an Italian guy that basically developed these cells, right? So I'll talk about delta G later and the spontaneity of the reaction. But let's just go, and then an electrolytic cell, right? So a voltaic cell, what you need to know, a voltaic cell or a galvanic cell uses a chemical redox reaction to generate electrical energy. So you remember the simple Daniell cell with the zinc and copper, right? So I'll show you that just now. But an electrolytic cell uses electrical energy to drive a reaction. So in an electrolytic cell, you need to put a battery for that cell to work, right? So like when you want a cell to work and you're providing energy, that's what we call an electrolytic cell, right? So here's a nice picture of a cell. Now you can see the zinc and you can see the copper metal, right? So this is the Daniell cell that we talk about, right? Now the voltage is reading 1.1 volt. So that means you can see there's a copper in copper sulfate solution and a zinc in zinc sulfate solution. And that's because you call them electrolytes, and you can see they're connected by the salt bridge here. All right. So that means now you got so something is being oxidized and something is being reduced. And here they're saying zinc anode oxidation. So from this, we can see that zinc is going to undergo oxidation and copper is going to undergo. So this is actually the setup. This is the cell setup. And this is an example of a voltaic cell or a galvanic cell, right? So you have, remember, when you have this setup, you're going to have oxidation and you're going to have reduction. So let's see what happens. So in the voltaic cell, the reaction of zinc with copper solution. Okay. I'm just going to skip all of this and I'm going to go to the reaction. So if you look at this illustration here, right, you know that the zinc strip now, zinc is being oxidized. Can you see the zinc metal is producing Zn2 plus? There we see that there. And then when the Zn2 plus, you can see electrons are moving in the external circuit. The electrons can't enter the solution, right? But the ions are forming in solution. And when the electrons move to the copper electrode, right, the electrode becomes negatively charged, and the copper from solution now starts getting reduced on the copper. So that is what's happening. So that means zinc gets oxidized, and on the copper, you get copper getting reduced. Okay, so that's what happens. So you have an oxidation half reaction at the anode, and you have a reduction cathode reaction that's taking place. So let's see how. There's the reaction. So on the left-hand electrode, if I go here, the left-hand electrode, LHS, and the right-hand electrode, and if I go to the actual picture, here's the copper, which is the right-hand electrode. Physically, it's the right-hand electrode, and the zinc is the left-hand electrode. So you're seeing a picture of that. Then I'm showing you a diagram of that, right? And now I'm showing you the reaction, so you can see the reaction. The zinc metal, right? You saw it getting oxidized to Zn2 plus, and the copper getting reduced to copper metal. I don't know. Yeah, in that picture we didn't really see it clearly. Let's see if we're seeing it. Oh yeah, you can't really see it, but you'll actually see copper getting. Yeah, you can see it here at the bottom. Some of the copper being deposited oil. You'll see like a reddish precipitate. Copper is not blue, right? If it's blue, then it's the copper solution. So you'll see the reddish precipitate on that there. Now, so oxidation, reduction, and here's the reactions. So oxidation taking place at the anode, it'll be negatively charged. Why will it be negatively charged? Because there's electrons moving away from it. That's why the anode is always negatively charged and the cathode is always positively charged. So you can see the minus and the plus. So they can ask you to draw a diagram, and they can ask you to show the cell notation, right? So you can see Zn2 plus increases, and there's the half reaction. Zn going to Zn2 plus 2 electrons, and at the anode, you can, that was at the anode. At the cathode, you can see copper getting reduced to copper. So this is all you need to know about. And let's see how we do the calculations, okay? So let's see. So you know about the Sol bridge, it completes the circuit, okay? So you can read about that. Right, so how does a voltaic cell work? And you're seeing the picture again. You know that electrons move from the zinc to the copper, and then we're reading this voltage. So can you see the electrons are moving through this voltmeter, and that's how we know electrons are going towards the copper. Okay, now I want to do the calculation. That's what I want you to know in terms of the calculation. Right, so let's see how we work out the cell potential. So you can see the overall cell potential is 1,1 volt, and E naught of the cell is greater than 0. Right, so we know it's a positive spontaneous reaction, right? So if the E cell is greater than 0, it's a spontaneous reaction. Right, now we talk about standard cell potentials. So you know this thing about the E naught value. So the E naught value, that means the E naught meaning at standard conditions, and standard conditions mean at 298 Kelvin, 1 atmosphere, and 1 molar solutions. That means if I'm carrying this out at standard conditions, I'm using 1 molar solutions. The atmosphere is 1 atmosphere, and the temperature is 298 Kelvin or 25 degrees. I will get this value here. So let's see how we get it. E cell is equal to E naught oxidation plus E naught reduction, right? And if you take the E naught values from the standard reduction potential table, then you will get this. So you can actually look at the E naught values from your standard potential reduction or your reduction potential tables, right? So you can work out the E naught cell. That means the E naught of the oxidation plus the E naught of the reduction cell, okay? So the sum of the half cell potentials, E naught of anode and the half cell potential of the cathode, you can now basically add the two. And so you may have also learned that E naught cell is equal to the E right-hand electrode minus the E left-hand electrode. You'll come to the same answer. So if you say E naught cell is equal to E naught right-hand electrode minus E naught left-hand electrode, you'll get the same answer. Okay, so there is a standard hydrogen electrode. And so this is the standard reduction potential table. So I just wanted to work out the coppers. There's copper 2 plus. Can you see it's plus 0.30 volts? It's written as a reduction. Okay. And let's look at the zinc. Where's zinc? Oh, zinc is not at, is zinc here? Let me see if zinc is, yeah. Okay. So this is the standard reduction potential. Okay. So you may have been taught for E naught values. So if I take my redox cell, okay, if I take my redox cell here, right, I'm coming back to this here. E naught cell is going to be E, okay, it's going to be E oxidation potential, right? So it's going to be E right-hand electrode, which is going to be plus 0.3 volts. Remember, I told you there's a way of calculating it, right? So it's the half cell potential of the anode and the half cell potential of the cathode. But if you're using a reduction potential table, you're going to say E right-hand electrode minus E left-hand electrode. So the E naught of the right-hand electrode is plus 0.34 minus E left-hand electrode will be minus 0.763 volts. I know that value, that's why I'm giving it to you. So plus 0.34 minus into minus 0.763 volts will give you 1.1 volt. All I'm saying to you here is you can calculate the E naught cell in two ways. The E naught of the half cell of the oxidation potential and the E naught of the reduction potential. But you may have been taught how to calculate the E naught cell of the E right-hand electrode minus the E naught of the left-hand electrode. And there you would use the standard reduction potentials. Okay, so please look at an example of that. And here is the standard reduction potentials that you would use for the electrochem, right? So remember, if the E cell is greater than 0, it is a spontaneous reaction. So remember I said E naught, that was the standard conditions. But when you're calculating standard EMF of the cells, standard, right? EMF of the cells, right? So you can see calculation of cell potentials. So the E naught values for the reduction half reaction and the sign must be reversed when using for an oxidation half reaction. What does that mean? Please look at this here, right? In this case, when you're changing stoichiometric coefficients, does not change the value of the E naught, okay? So if you got a reduction potential here, you don't multiply 0.791 by 3, right? Remember that. So I want to show you this example. Please look at this example. Determine the E cell or the cell reaction and the cell potential for a cell based on the following half reactions. So you got the two reduction reactions here, right? So let's look at this example here, okay? Because I don't have okay, so in this case, let me just see if I have the standard reduction potentials on my, I've got Ag and I've got lithium, right? Okay, so I'm going to use this example here. Okay, so determine the cell, it's supposed to, in this case, it's supposed to be determine the standard cell reaction, right? Determine the cell reaction and the cell potential for a cell based on the following half reactions. So if I say at standard conditions, I'm going to use this standard reduction potential table here, right? The standard potential table here. I want to show you something, so please pay attention. In this reaction here, I've got lithium plus going to E naught going to lithium, and I got Ag plus E naught going to Ag. Now, if I connect these two here, I want to know whether lithium will get reduced by silver or silver will get reduced by lithium, right? So how do I know that here? How do I know that here? So I want to show you this and remember this, what I'm saying to you. I'm going to say this very, very carefully. When you look at the table, can you see lithium plus E naught going to lithium solid? And it got a negative potential. And silver plus E naught going to plus, right? When you see a negative E naught value, it means that the lithium will go to lithium plus. That means it doesn't like to undergo reduction. So when you see a negative value, the lithium will not be reduced, it'll be oxidized, right? When you see a more positive value, so that means silver likes to undergo reduction. Remember that, write this down. The more positive the standard E naught value, it undergoes reduction. The more negative a standard reduction potential, it undergoes oxidation. So let's go back to that example. So in this example here, lithium will undergo the reverse reaction. So you will write Li solid going to Li plus E electrons and Ag plus. So then you can write the overall reaction, Li solid plus Ag plus going to Li plus Ag solid. Okay, that's how I used the standard reduction potential. So I want you to write this down. Li, that means this top reaction will be reversed. How do I know that? It's got a more negative E naught value. This will remain as is because it's got a more positive plus 0.8 volts, right? And the Li was negative from this, was negative 3.05 volts, right? So in this reaction here, I looked at the standard reduction potential and the Ag plus E naught going to Ag plus had a value of plus 0.8 volts. That means it gets reduced. Because Li, this value was negative 3.05 volts, this reaction will be reversed. So then the overall reaction is Li solid plus Ag plus going to Ag solid plus Li plus. So how do I calculate the E naught? The E naught is going to be E right-hand electrode, and whenever the reduction takes place at the right-hand electrode, so it's going to be plus 0.8 volts minus into minus, right, negative 3.08 volts, and we can work out the E naught value. So all I wanted you to note that looking at the reduction potentials, you will know what undergoes oxidation and what undergoes reduction using the standard reduction potentials. So here, look at this example. A cell can be prepared from copper and tin. What is the E naught for the cell that forms the following half reactions? So here, you can see copper has got a more positive E naught and tin has got a less positive or a more negative E naught. So because copper has got the more positive E naught, it undergoes reduction. And because this has a less positive, it's going to undergo oxidation. So here you reverse this reaction. So it will read Sn2 plus going to Sn4 plus 2 electrons. And then you're going to have E naught cell is going to be, right, is going to be 0.3 volts minus into minus 0.13 volts. And you can get, I think your answer here is B, 0.21 volts. Okay, so whenever you see the E naught value, the more positive the E naught value, you will write it as a reduction potential. If you remember this, you will not have problems with your redox calculations. So whenever you're calculating E naught, it will only be from the standard reduction potentials. So use my method. E naught cell is equal to E right hand electrode or E cathode. That's where the reduction is taking place, minus E left hand electrode or E anode, where the oxidation takes place. Okay. So I want you to remember that whenever you're working out E naught cell, you're going to use the standard reduction potential. So E naught cell is equal to E cathode, sorry, minus E anode. And the more positive the E naught value, it remains as is. So in this reaction, copper will remain as the reduction. So your E naught cell is going to be 0.34 volts minus into 0.13 volts. Okay, so you can see that you basically have E cathode minus E anode, and you can get the voltages. So that's going to be B 0.21 volts. So whenever you're calculating E naught, which is that standard condition, you will only use the standard reduction table. Okay. Here's another example which you can calculate. So the E, as you can see, in this case, immediately the positive value will be written as is, the negative value will be reversed. Okay. So Cr going to Cr3 plus is the anode or the oxidation. So you will not get these particular problems incorrect. Okay. So it's quite easy to work out the E naught values. And here, look at this here. Which is the strongest oxidizing agent? So which has got the highest E naught value, right? So the most positive E naught value. And you can see the most positive E naught value is obviously 0.4 is going to be negative 0.28, because the most negative is 2.89 volts. The most positive is negative 0.28 volts. So cobalt E is basically the strongest oxidizing agent, right? That means it gets reduced and it's written as is. Okay. No, I'm incorrect. I'm incorrect. So we're looking for select the strongest oxidizing agent, which means what gets reduced. So you've got to remember your terminology. The strongest oxidizing agent that gets reduced will have the most negative E naught value. And this case, it's going to be Sr2 plus. Okay. So remember I said the most negative. No, I'm mixing myself up. I'm even getting confused myself. So let me just say that again. The strongest oxidizing agent that gets reduced. So I am correct. Okay. The strongest oxidizing agent that gets reduced, that means the reduction reaction that's written as is. So in this case, I said the E naught value with the most negative value, right? The most negative value. If you have the most negative value, it will be the oxidizing agent, right? So the most negative value will be the oxidizing agent. The most positive will be the reducing agent that gets oxidized. Okay. So in this case, the oxidizing agent, right? In this case, the strongest oxidizing agent that gets reduced should have the least negative value. Now, this can be a bit nauseating because we're working with negative values. So think of the Daniel cell. Zinc had a negative value, it gets oxidized. Copper had a positive value, it gets reduced. So in this case, we're looking for the oxidizing agent that gets reduced. So it's going to have the most positive value. So I was right initially that cobalt has got the most positive value. So it's the oxidizing agent that gets reduced, right? So the oxidizing agent gets reduced and it'll have the most positive E naught value. And in this case, you can see negative 0.28 has got the most positive value, right? So sometimes you can see it can get a bit tongue twisting, but you have to understand that, okay? So in this case, if it said, which is the strongest reducing agent that gets oxidized, then you can see strontium will be the most negative. That means it'll undergo oxidation. So it becomes the reducing agent. Then this reaction will be reduced in an electrochemical cell. Okay, so in this case here, cobalt was the right answer. Okay, so here, again, can you see a galvanic cell consists of an iron electrode and a silver electrode. Whenever you see the word standard EMF, it's going to be E naught like this. It's going to be E with the E naught cell. That's standard conditions, and you're going to use the standard reduction table. Okay. Now, if you do it under if you're going to do so, I see E naught cell. That means in this case, is the following reaction as spontaneous as written? So you're going to calculate the E naught of the cell, and you're going to look for the E naught of the reduction of iron and the reduction. And in this case, you can see iron 2 is getting, so iron 2 gets reduced and iron 2 gets oxidized. It's a bit of a twisty one, this. So you're going to look at the standard reduction table for iron 2 getting oxidized to iron 3 and iron 2 getting reduced. Okay, so you can look at this particular example, right? Now, so all of these, we said you're working under standard conditions. So I think you are familiar with the line notation, and you can see here you got the right-hand side electrode, and this is the Daniel cell. So you got the left-hand electrode. So you write the anode, and then there's the there's the anode compartment with zinc and Zn2+. There's the cathode compartment with Cu2+ and Cu, and then the solid lines represent the barrier. The double line is the salt bridge, and the single lines are the shows the physical barrier. So remember this here, what I showed you. So there's the zinc anode, so Zn solid, and the Zn2+ in solution is what we show Zn. So the solid line shows the barrier. That means you got a solid in the solution, and there's the salt bridge with the double line. So you can show it in what we call the line notation, right? So they may ask you, giving you this diagram to draw the line notation. So the right-hand electrode is copper, physically as it is, and the left-hand electrode is the zinc, right? So you should know how to write the right-hand electrode and the left-hand electrode and doing calculations. So here they give you a line notation, and they can ask you, which is the anode? So you know, obviously you know that the right-hand electrode undergoes reduction, the left-hand electrode undergoes oxidation. So like in this here, see the zinc and the copper. So right-hand electrode undergoes reduction, the left-hand electrode undergoes oxidation. So as it's written here, which of the following reactions occurs at the anode? Here's A, aluminium getting oxidized to aluminium 3+, because that's the left-hand electrode, which is the anode, and it undergoes oxidation. So get all of those terminologies right and how it works. Go through these examples. Okay. I know it's a bit difficult, and it's a bit time consuming for you to go all of this. And then I think for delta G naught, you know how to work out delta G naught. So can you see you got -N, that was the number of moles of electrons. F is the Faraday constant, and this E naught is what you work out from your standard reduction potentials. So in your examples, they'll ask you, so calculate the delta G naught for the previous example. So in your example, they'll give you the cell, you've got to work out the E naught, and N comes from your number of electrons involved in the redox. F is a constant. So if delta G naught is negative, it's spontaneous. If delta G naught is positive, it's non-spontaneous. So you know how to do those calculations. Okay, so here you can see, calculate the standard Gibbs energy change. So whenever it says standard, it's got a little superscript 0, and you're going to use the E naught at standard conditions using the standard reduction potentials. Okay, So go through my examples and you'll see these calculations will help you for your calculations of E naught. All right. I'm not too sure whether you did determining the equilibrium constants, but go through the calculations for Gibbs free energy changes. Okay. So remember, the E naught of cell is generally, if you are given the delta G naught, you can calculate the E naught of the cell from the Faraday constants. And this tells you exactly how to E naught of the cell, the delta G, and the equilibrium constants. I think you're quite familiar with that. The last thing I just want to spend time is the Nernst equation. And all of these times, I've been talking about delta G naught. I've been talking about E naught, which is under standard conditions. When you use the Nernst equation, it's going to be under non-standard conditions. And you are familiar with this. E is equal to E naught minus 0,0592 over N log Q. So you are now calculating the E of the cell under non-standard conditions. And that's where you would use the Nernst equation. This is the Nernst equation, okay? You've got to know this and you've got to know how to calculate. So in this case, calculate the voltage produced by the cell at 25 degrees. So if you're using the Nernst equation, that is, now you're going to know the E naught. So you have to calculate, they'll generally give you the E naught at standard conditions. So you can see they've given you the concentrations of aluminium and the concentration of cobalt. So in this equation here, you've got the E naught. The log Q is simply going to be your products, which is CO. So you got to find out which is the product and which is the reactant, right? So remember, you got, this is the cathode and this is the anode. So when you write out the overall reaction, so you're going to find out which is the products and which are the reactants from the cell reaction. Okay, so you need to go over that and look at using the Nernst equation and how to apply the Nernst equation. All right, so go through the Nernst equation and you're going to look at, in this case here, I told you, if you are using the Nernst equation, you know how to use E naught, and log Q will simply come from understanding you're basically going to write the products over the reactants. So you're going to write the overall reaction and you're going to write what gets oxidized and what gets reduced. And that you will learn from your standard reduction table. Okay, so in this case, you will get the E naught value. So look at the standard reduction for aluminium and aluminium 3+. Look at the standard reduction for cobalt and cobalt 2+. Find out which is the more negative E naught and find out which is the more positive E naught. The more negative will be the oxidation reaction. The more positive will be the reduction. Write out the overall equation and then you can work out Q for the change. So Q is actually it's going to be the concentration of your product over the concentration of your reactant. Okay, the E naught will either be given or you can work it out from the standard reduction table. And you can calculate the cell under standard state conditions using the Nernst equation. So you can calculate, before this we were calculating under standard conditions using the reduction table. Then you're going to calculate using the Nernst equation under standard state conditions, meaning they'll give you the concentrations of the aluminium and the reactants and the products that you have here. Okay, so you can go over those examples. And then you have electrolytic cells. Remember, we told you that if you have a negative E naught, then you're going to now reverse this reaction by providing an external source. So I don't think you will go through a lot of electrolytic cells, but in this case, you can see, sir, the E naught cell is negative. So you have to provide energy for this cell to work. And then it will, so that means if you provide an external energy source, the reverse reaction will take place. Okay, And then electrolysis is a reaction where you undergo, I think you may have done basically looking at electroplating and how to use electroplating and the laws of electroplating. So galvanolysis basically you can look at how to carry out electrolysis, which is an example of an electrolytic cell. So when you do galvanizing, you're using an electrolytic cell, right? So you're providing an energy. So for example, in this case, you can see the reaction won't take place. So you've got to produce an external supply for it to take place. And in the galvanizing industry, you carry out electrolysis. Okay, so go through the electrolysis. I think you've been through all of this in your notes, but I just wanted to put it in sort of perspective for electrochem. So you'll work out E naught from the standard reduction tables. You will work out the E cell from standard states, and then you do delta G naught, the Gibbs free energy change, right? And then you will do electrolysis using electrolytic cells. Okay, so please go over these notes and use your notes, and you'll be able to work out all of these calculations. I do understand it's been a bit, you know, unfortunately, I've had to like sort of go through all of these things in one go, but I know most of you sort of would have picked up here and there on what I've been discussing with you. All right, in terms of electrochem. So just to recap electrochem, remember change in oxidation number, identify oxidation and reduction, look at the balanced redox equation, look at the standard reduction potential, identify what's been oxidized, what's been reduced, write out the overall cell equation, and then you can work out the E naught under standard conditions. Okay, once you know that, then you can calculate the E naught values and then go to the standard state conditions. All right, I'm going to end off there, and I'm going to basically post up these notes. In fact, these notes are posted, so you can go through them. And if you have any queries, you can email us and we can help you with these. But use your notes and use these notes. They're quite useful, and you'll be able to get an understanding of it. Okay, so good luck in your papers. And I'm definitely really I have a very I have no doubt that you'll be able to score good marks in chemical equilibrium, acids and bases, and electrochemistry, and get those questions right. I've covered all of those questions that you would get in your calculations in your papers. So good luck, everybody, and study hard. You've got to. Okay, there was one question: how to identify an anode and a cathode in a balanced equation? I told you, if you looked at the reaction, on your physical setup of your cell, the cathode will always be the right-hand electrode, the anode will always be the left-hand electrode. From the standard reduction potential, whenever you have a positive E naught value, it's the cathode, and when it's a negative, it's the anode. Now, when I say positive and negative, you can have two positive values, but one is more positive and one is less positive or more negative. You understand what I'm saying? It's a relative term. So look at the standard reduction potential, right? You can also have two negative values, like I showed you in one of those calculations. The one that's more negative will be the anode, and the one that's less negative will be the cathode. So just remember, E cell or E naught is E right-hand electrode minus E left-hand electrode. The E right-hand electrode is the cathode, the left-hand electrode is the anode. Okay, so go through the examples of those. Right, so no, only in galvanic cells. We're only talking about galvanic cells. Okay, so yeah, the same will be on electrolytic cells. So just remember, with electrolytic cells, you'll have to provide an external source for the reaction to reverse, because you want the reverse of that reaction. Okay, for it to go into that positive spontaneous mode. Okay. Yeah, I think just go through the notes, and most of your questions I think will be in those calculations. Okay. Good luck, guys, and study hard. You're gonna do well.
Okay, thank you so much, Ajay. I just want you guys to know that I'm going to upload the notes. I'm going to ask the webpage administrator to put the notes up. So I'll drop a link to all of Ajay's notes and some solutions as well, and also some past papers. Just keep an eye out for the webpage that I've been circulating on the chat, and you can get the stuff from there. Thank you so much for attending and staying to the end. I hope it's been useful to you. And we see you in future sessions. Also keep an eye out on the webpage for sessions that might be arranged later on. But if I have your email addresses, if you've recorded the register, give me an email address. I will send you regular email updates to when sessions will take place and when new material is posted up. Thank you for attending. If you have any more questions about the program, you can put them in the chat. I'll answer. I'm just going to play you a short video on how to apply for university.
Part of the UKZN experience is the opportunity to be part of a community and to network with not only our world-renowned academics, but with future game changers and leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply. All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student residence application. The application process is as follows. Step 1. Consult the CAO handbook. This handbook provides a list of all qualifications available at UKZN. Step 2. Have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3. Find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westville. Then BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za. It's that easy. Pay close attention to closing dates for qualifications. For example, MBCHB closes on the 30th of June, whilst other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.
Okay, guys, I'm going to end the session now. Thanks, Shabazz.
Yeah, I'll see you, Ashwin. Have a good weekend.
Okay, cheers. Bye-bye.